Okay, so we have an electrodynamics practice final exam, so let's get right into it. Number one, a thin rod of length 2L lies on the z-axis from z equals negative L to z equals L. It has uniform charge density lambda. Find the electric field at the point A, 0, 0. Okay, so let's see what we could do here. So we have an electric field of a charged rod. The rod lies from z equals negative L to z equals L. Point is A, 0, 0. Okay, so I'm going to go through this relatively quickly. I'm not going to go over all the computational stuff with intermediary steps with some calculus, algebra, arithmetic, etc. So just so you have this as a reference for practice. So a charge element is dq equals lambda dz. We say the distance from dq to the point is r equals square root of a squared plus z squared. And by symmetry, the z components cancel. So only the x component remains, okay? So right there we have the x component, that dx component of the electric field. That's going to be 1 over that 4 pi times the permittivity of free space, okay, E naught, or epsilon naught, times lambda a dz over a squared plus z squared raised to the 3/2. Okay. Now that's after substituting. So what we're going to do now is we're going to integrate. We're going to say that e sub x, that equals lambda a over 4 pi epsilon naught from negative L to L as the bounds limits of integration. So there's our interval from negative L to L. So we're integrating dz over a squared plus z squared to the 3/2. So when we integrate that, that's going to come out to z over the quantity a squared times the quantity square root of a squared plus z squared. So that e sub x there equals lambda a over 4 pi epsilon naught. And we are evaluating from negative L to L. So when we do that, we're going to get e sub x equals lambda a over 4 pi epsilon naught times 2L over a squared times the quantity square root of a squared plus L squared. So therefore we have that electric field right there. That's going to be 1 over 4 pi times the permittivity of free space times 2 lambda L over a times the quantity square root of a squared plus L squared times that x hat. Okay, so that takes care of number one. Okay, so moving along to number two. So that's number one. Number two. Focus. Okay, so number two, here's what we have here. So for number two, we have a solid sphere of radius r has charge density rho of r, and that is equal to p naught times 1 minus r squared, lowercase r squared over capital R squared. Okay, so for lowercase r is less than or equal to capital R. Okay, so remember, just lowercase r, that's the radial distance from the center or origin, and r being a fixed capital R fixed radius, and if rho equals 0 on the outside. So find E of r for A, lowercase r less than uppercase R, B, lowercase r greater than uppercase R. So here's what we could do. We employ Gauss's law with uniform charge density. So that's that notation here. This function of r equals rho naught times 1 minus r squared over capital R squared. By spherical symmetry, the electric field, that is equal to that E of r times r hat. And I apologize if I misspeak, or if I say the symbols too fast. So letter A inside, lowercase r is less than capital R, so we're going to use Gauss's law So we're going to substitute that. This is going to be E of 4 pi r squared. Okay, that's going to be Q sub ENC. That's the enclosed charge inside the Gaussian. That's the enclosed charge inside the Gaussian surface over the permittivity of free space, epsilon naught. So the enclosed charge is as follows here. Q sub ENC from 0 to r, rho of r prime times 4 pi, r prime squared, dr prime. And that Q sub ENC becomes this, that 4 pi rho naught from 0 to r, quantity 1 minus r prime squared over uppercase r squared times r prime squared dr prime. Okay, so just moving along up here for our Q sub ENC, our enclosed charge inside the Gaussian surface, we get 4 pi times P naught times the quantity r cubed over 3 minus r to the 5th over 5 capital R squared. So therefore, E of 4 pi r squared, okay, that's going to be 4 pi rho naught over epsilon naught times quantity r cubed minus over 3 minus r to the 5th over 5 capital R squared. So what we're going to get here for our electric field magnitude as a function of its radius, we're going to get rho naught over epsilon naught times the quantity r over 3 minus r cubed over 5 capital R squared, and then r hat, comma, that is where our lowercase r is less than our uppercase r. So the electric field we could also write as rho naught over epsilon naught times the quantity r over 3 minus r cubed over 5 capital R squared times that r hat. So this would be for part A, for r is less than r. R is less than capital R. Okay, and we're continuing on the next page. So let me just get this set up for number 2. So for number 2, continue now for part B. We want outside where lowercase r is greater than capital R. So again, we want to find the total charge. So our Q equals 4 pi rho naught from 0 to capital R of 1 minus r prime squared over capital R squared times r prime squared dr prime. Okay, so evaluating that integral, we're going to get Q equals 4 pi rho naught times the quantity capital R cubed over 3 minus capital R cubed over 5. That's going to come down to, when we do the computation, this charge would be 8 pi over 15 rho naught r cubed. Okay, so what we're going to get here for r is greater than capital R, E of 4 pi r squared is going to equal Q over the permittivity of free space. So we wind up with E of r is 1 over 4 pi E naught times Q over r squared, and that's going to equal 2 pi naught r capital R cubed over 15 E naught r squared times r hat, and this is where r is greater than r. I don't know if I misspoke. That's rho naught there. That's epsilon naught there. And then our electric field is going to be 2 rho naught times capital R cubed over 15 epsilon naught r squared r hat, where r is going to be greater than lowercase r is going to be greater than capital R. So that takes care of number 2, and we can now move on to number 3. So moving along to number 3, we're going to have a spherical shell. So for number 3, we have a spherical shell of radius r, and that carries a surface charge density here we're given that function. Okay, find the electrostatic potential inside and outside of the sphere. So here's the electrostatic potential for this spherical shell. So here's what we're given. And because of the angular dependence is cosine of theta is p sub 1 times cosine of theta, it only the L equals 1 term is going to appear. Okay, so the general solutions for this are going to be inside V sub in is A times the quantity R cosine theta, and outside is going to be V sub out is B cosine theta over R squared. So the potential is going to be continuous where lowercase r equals capital R. So AR cosine theta, that's going to equal B cosine theta over capital R squared. So RB, that's going to equal AR cubed. So moving along here, the electric field is going to satisfy the boundary conditions. When we have this, we're going to say E sub out R minus E sub in R equals our condition here. So here we have E sub R over this partial derivative negative dV dr, where we have E sub in R equals negative A cosine theta. So for the outside, we get BR, the negative 2 cosine theta. E out R equals that negative partial derivative dV dr, that out, and that's over this negative rather, this negative partial derivative dV out sub out dr, that's going to be 2b cosine theta over R cubed. And now if we let R equal capital R, E out R, that's going to be 2b over capital R cubed cosine theta equals 2a cosine theta. And now from here, we could say that 2a cosine theta minus a negative a cosine theta, that equals, okay, that's going to be that the charge cosine theta over E naught. So that 3a equals that charge naught over epsilon naught. A equals the charge naught over 3 E naught. Okay, so, and this is related to the charge density, I should say. So therefore, okay, V sub in equals the charge naught over 3 epsilon naught R cosine theta, and B is A R cubed equals that charge naught R cubed over 3 epsilon naught, and here's what we get for our V sub out. The charge naught R cubed over 3 epsilon naught times cosine theta over R squared. So basically, spherical ball, radius R carries that surface charge density. Okay, find the electrostatic potential inside, outside the sphere. That is for the outside, and we are all set because we got the in and we got the out. We got both. Okay, so pardon me if I abbreviated some expressions by speaking, but this is the math for number 3. Okay, number 4. Let's get into number 4. Okay, so we got a point charge Q. Whoops, sorry. So, sorry about that. Point charge number 4. A point charge Q is located at distance d above an infinite grounded conducting plane. Find the potential above the plane. So let's do part A. So method of images, charge near a grounded plane. Let the grounded plane be z equals 0. The real charge Q is at z equals d. We're going to replace the conductor with an image charge, negative Q at z equals negative d. So part A, potential above the plane. Okay, so the potential above the plane for z is greater than 0 for this multivariable function v of x, y, z. this is going to be 1 over 4 pi epsilon naught times this quantity, q over square root of x squared plus y squared plus z minus d squared minus q over x plus x squared plus y squared plus z plus d squared. So at z equals 0, both distances are equal, so v equals 0 as required. Okay? So find the potential above the plane. Well, that's basically, we got it. Okay? For part B, find the induced surface charge density on the plane right here. So, induced surface charge density, okay, that's going to equal this negative epsilon naught, and then the partial derivative there, dv dz, z equals 0 positive. So S equals, S squared rather equals x squared plus y squared. So, since S squared equals x squared plus y squared, then we could substitute, right? S squared here and S squared here, and rewrite this term as that. And then we differentiate it. I'm not going to say this all out loud because it's right here. Here's the partial derivative, dv dz, it equals this. Okay, after you do that, plug in that z equals 0. When we evaluate it, it's going to equal this. Okay, so we wind up with the induced surface charge density is going to equal in the end negative qd over 2 pi, and that's the quantity s squared plus d squared raised to the 3 over 2. So that's raised to the 3 over 2. And that is for part A. Part B. Part C, find the force on the charge. So finding the force on the charge for this. For part C, what we do here, force on the charge, the real charge feels the force from the image charge negative q, separated by a distance of 2d. So F is equal to 1 over 4 pi e epsilon naught times q times negative q over 2d squared. Finding the magnitude of that for our force, that's going to be just q squared over 16 pi epsilon naught d squared. And remember here in this situation, direction is downward toward the plane. Since it's the direction is downward toward the plane, it's going to be F is negative q squared over 16 pi times the permittivity of free space times d squared times that z hat. So that takes care of number 4. Let's move into number 5. So number 5, let's see what we have here. Okay, so number 5, a grounded conducting sphere of radius r is placed in an initially uniform electric field. E naught is equal to E naught times Z hat. Find the potential inside the sphere and induced surface charge density. So we have a conducting sphere in a uniform electric shell. In a uniform electric field. A grounded conducting sphere of radius r is placed in a uniform field, and we get this. E naught equals E naught Z hat. Far away, the potential should approach V is approaching negative E naught r cosine theta. The outside solution has the form V sub out equals quantity AR plus B over R squared cosine theta. Far away, A equals negative E naught, so V sub out equals negative E naught R plus B over R squared times cosine theta. Now because the sphere is grounded, V of capital R comma theta, that equals 0. So negative E naught capital R plus B over capital R squared equals 0, and B would equal E naught capital R cubed. So thus, V sub out equals negative E naught times quantity lowercase r minus capital R cubed over lowercase r squared times cosine theta. Okay, so inside the conductor, that's out in, V sub in equals 0. Okay, and the surface charge density what we get is that surface charge density is epsilon naught E sub out comma R of capital R. So E sub R, that's going to equal the partial derivative of negative, that's negative dV dr. And then dV dr, if we find that partial, that's negative E naught, parentheses 1 plus 2 capital R cubed over lowercase r cubed times cosine theta. So our E sub R equals E naught times the quantity 1 plus 2 capital R cubed over r cubed times cosine theta. And we evaluate at r equals, lowercase r equals capital R. E sub R of capital R equals 3 E naught cosine theta. Therefore, that induced surface charge density is 3 epsilon naught capital E naught cosine theta. So that's what we get for that. Pardon me if I'm talking quickly. It's because you can always pause the video. You could always do these on your own and just check, or, so these are fun. Okay. Electrodynamics is fun. Okay, so here, solid sphere of radius r carries uniform, this is number 6, a solid sphere of radius r carries uniform charge density rho naught. Okay, now part A, find the total charge. So part A is right here, total charge. What we could do, energy stored in a charged sphere. Uniformly charged solid sphere is what we have. Total charge is going to be Q equals rho naught times 4/3 pi capital R cubed volume of a sphere. And that's R cubed. Part B, find the electric field everywhere. The electric field inside would be Q sub E and C. That's our enclosed charge inside the Gaussian surface. That equals rho naught times 4/3 pi r cubed. So E of 4 pi r squared, that's Q sub E and C over epsilon naught. And that's going to give us E equals P naught R over 3 epsilon naught. So our electric field here is P naught R over 3 epsilon naught. R hat, where lowercase r is less than capital R. And outside the electric field is going to be 1 over 4 pi epsilon naught Q over R squared, R hat, where R is greater than capital R. And for part C here, find the total electrostatic energy stored in the field. Well, what we could do there, electrostatic energy, we could use this integral. U equals E epsilon naught over 2 times the integral evaluated E squared. That's d tau. So from here, inside contribution, U sub n is epsilon over 2 from 0 to r, P naught R over 3 epsilon naught squared, 4 pi r squared dr. So that's going to be this integral, 2 pi rho naught squared over 9 epsilon naught from 0 to capital R, lowercase r to the 4th dr. And when you evaluate that, U sub n, you're going to wind up with 2 pi rho naught squared capital R to the 5th over 45 epsilon naught. Okay, so let's do the outside contribution. So the outside contribution now for number 6. So the outside contribution, U sub out, we get epsilon over 2 from r to infinity of 1 over 4 pi epsilon naught minus Q over r squared, 4 pi r squared dr. Well, simplifying this, U out, it's going to equal this. Q squared over 8 pi epsilon naught from r to infinity dr over r squared. So evaluating that, U sub out would be Q squared over 8 pi epsilon naught times capital R. And since Q equals 4 pi r cubed rho naught over 3, we could write the total energy in terms of Q. U equals 3 Q squared over 20 pi epsilon naught times R, or equivalent form, U equals 4 pi rho naught squared, capital R to the fifth, over 15 epsilon naught. So this takes care of number 6. And now we can move along to number 7. Okay, number 7, we have a localized charge distribution as total charge 0 and electric dipole moment. And here we have our electric dipole moment here, right? The leading order potential far from the distribution. So dipole approximation here, given total charge 0 and dipole moment, our far field potential, the leading order potential of a dipole is this, V of R comma theta 1 over 4 pi epsilon naught times rho cosine theta over r squared. That's all for letter A. For letter B, find the corresponding electric field. Electric field, we're going to use spherical coordinates. E sub r equals negative partial derivative dv dr. E sub theta equals negative 1 over r partial derivative dv d theta. And for V, that equals rho cosine theta over 4 pi epsilon r squared. So E sub r equals 2 rho cosine theta over 4 pi epsilon naught r cubed. And epsilon sub theta equals rho sine theta over 4 pi epsilon naught r cubed. So our electric field that corresponds to this is 1 over 4 pi E naught epsilon naught rho over r cubed times the quantity 2 cosine theta r hat plus sine theta theta hat. Okay. That's a plus sine theta theta hat. Sorry about that. Letter C, explain physically why the monopole term vanishes. So for C, the monopole term vanishes. It depends on the total charge. V sub monopole is 1 over 4 pi epsilon naught times Q over R. And since the total charge is 0, the monopole contribution, Q equals 0, vanishes. The dipole term is therefore the leading term. So that takes care of number 8. Moving along to that was number 7. Moving along to number 8. Number 8, we have a straight wire segment lies on the z-axis from z equals negative L to z equals L, carrying steady current I in the positive z hat direction. Find the magnetic field at the point A, comma, 0, 0. So magnetic field of a finite wire. Okay, the wire lies on the z-axis from negative L to L. Point is A, 0, 0. We use Biot-Savart law. So dB is U naught over 4 pi, and then times the capital I, dl cross capital R over R cubed. Here that dl is dzz hat, and capital R is ax hat minus zz hat. So doing the math, dl cross R is dzz hat cross ax hat minus zz hat, and that's going to be a dz y hat when we do the computation. So this dB sub y is equal to u naught I over 4 pi times a dz over a squared plus c squared to the 3 halves. And we integrate, referring to problem 1, very similar integral. B sub y of u naught I over 4 pi. When we integrate here, we're going to wind up with b sub y equals u naught I over 4 pi times 2L over a squared times the quantity square root of a squared plus L squared. So here is our magnetic field right here. It's going to be magnetic field is u naught I over 4 pi times 2L over a times square root of a squared plus L squared in times that y hat. Okay, so that takes care of number 8. Number 8, and now we can go to number 9. Number 9. Oops. Sorry about that. Okay, so number 9, a long cylindrical wire of radius r carries current density. Thus J of r equals J naught, quantity 1 minus r squared over capital R squared z hat. 2 parts to this. Find the magnetic field, B of r, for A, R is less than capital R. B, R is greater than capital R. Okay, so let's see here. Okay, so we're going to use Ampere's law with non-uniform current density. That's the type of problem this is. So this J of R equals J naught, parentheses, 1 minus R squared over capital R squared Z hat. By cylindrical symmetry, that magnetic field is B sub phi of our phi hat, or phi, rather, phi. Ampere's law, here's what we have for Ampere's law, and then B of 2 pi R is U naught I sub E N C. So inside, R is less than capital R, that I E N C is equal to 0 to pi, this J of R prime, 2 pi R prime, dr prime. I sub E N C is 2 pi, J naught 0 to R, 1 minus R prime squared over capital R squared, R prime, dr prime. And we wind up with this after we integrate, okay? And so B of 2 pi R, we wind up with this. B of R equals this term, so capital B is U naught, J naught, R squared, R over 2 minus R cubed over 4 capital R squared quantity times phi hat. That's for A. And then for B, outside, lowercase r is greater than capital R. Total current, here's what we have. Okay, total current. I'm just going to go through this a little bit more quickly because you know these symbols if you've taken the course. And actually, this is just going to come out to capital B is U naught, J naught, R squared over 4R and times phi hat. So that takes care of number 9. Okay. Number 10, long solenoid of radius R carries n turns per unit length, and your current here, is I. So we want to find the magnetic field inside, okay? And our current, find the magnetic field inside and outside the solenoid. We're going to make this is part 1 of the video. I'm just going to pause this and we'll get into part 2.